So I'd like to sort of explore this question type here in particular. And the idea here is really to work backwards. So we want to find the exact angles, or really the exact values, of the cotangent of theta and the sine of theta with the information that we're given. And this question type in particular is not as difficult as the previous question type, but it does require some deductive reasoning. Um, and these are the answers here, and I'm going to actually show how we can work our way backwards to get to the same answer. So we're told first that that theta is an angle in quadrant 2, such that the secant of that angle, or theta, is equal to -9/4. So really what we're given here is we're given information regarding where this angle is. It's in fact going to be in quadrant 2. And so you can think of it something like this. And the angle which we would have as a result of the terminal side being in quadrant 2 would be like this. Now, so the secant of this particular triangle is equal to -9/4. And the goal is eventually to sort of take this triangle and replicate it off to the side. And what we eventually want to do is we want to essentially solve for each side of the triangle. And after doing that, the cotangent, which is just 1 over the tangent, or the sine, which is just the opposite over the hypotenuse, that is essentially where we would derive our exact values. So we know that the triangle looks something like this, and we're given the fact that the secant of theta is equal to -9/4, right? And we also know that the secant of theta is equal to 1 over the cosine of theta, right? Because we have sine, cosine, tangent, cosecant, secant, cotangent. And the cosecant of theta, if we were to look at SOHCAHTOA here, we would know that the cosine is the adjacent over the hypotenuse. So the secant of theta, being that it's 1 over the cosine, and we know that 1 over the cosine is, we know that the cosine is the adjacent over the hypotenuse. So this is the same thing as saying 1 over the adjacent over the hypotenuse, which is the same thing as saying h over a. So secant of theta is actually h over a. So really we can draw a parallel here and say that the secant of theta is equal to h over a in terms of its identity. So if we had a triangle here, and this was our opposite side, this was our hypotenuse, and this was our adjacent, the secant of theta would have a hypotenuse of 9. We're ignoring the sine here, but that's important to keep note of. And it's going to have an adjacent side of 4. So we can say that the hypotenuse, right? So the hypotenuse is 9, and the adjacent side is 4. And the opposite side, unfortunately, we do not know. So let's go ahead and label this, right? The hypotenuse is 9 and the adjacent is 4, and the opposite side is still in question. So what you want to understand is when we would try to find the cotangent of theta, we would actually just do 1 over the tangent of theta, and the tangent of theta is the opposite over the adjacent. So finding the opposite is imperative in this case if we want to put the opposite over the adjacent. So we want to solve for the opposite side. So we write solve for opposite, right? So we want to solve for the opposite side, and we're going to use the Pythagorean theorem, which says that h squared equals a squared plus o squared. And h squared in this case is 9, so that's 9 squared, equals a squared, which is just 4, so that's 4 squared, plus, let's go ahead and get that plus there. So it's going to be plus o squared. That's going to be 81 equals 16 plus O squared. And 81 minus 16 will equal O squared. And so if we want to do that off to the side, we know that we would have 5 here, 2 here. Let's see, or actually just a 6 rather, 65. So 65 equals O squared, which means O is actually going to be equal to 65. So in this case, it's going to be under root 65, which means O is equal to under root 65. So that's how we would use the Pythagorean theorem to solve for the remaining side. And the idea now is to recognize that the cotangent, right? So we're looking for the cotangent. The cotangent of theta is just 1 over the tangent of theta, which is the same thing as saying 1 over O over A, right? O over A, which is, of course, the same thing as saying A over O. So the tangent of theta is A, which is 4, over under root 65. But of course, we're going to rationalize the denominator. So we're going to multiply by 65 here. So we have 4 under root 65 over under root 60. Well, since we rationalize the denominator, we just have 65. And that would be our tangent of theta, right? So that is our tangent of theta. And similarly, we could do this. We could do a similar deduction for the sine of theta. And the sine of theta, let's see here, the sine of theta is simply going to be the opposite over the hypotenuse, and that would just be the opposite side, which is under root 65, over the hypotenuse, which is 9, and that would be our hypotenuse there, or the sine of theta rather. Now, an important thing to recognize is that we have negative in this answer, and it's not just for any random reason. We have the cotangent of theta is negative because in finding the cotangent of theta, which we did over here, we actually wanted to find the tangent of theta. And if you recall, the tangent of theta was O over A, and this O over A, the opposite over the adjacent, was actually the opposite over the adjacent of the triangle in the second quadrant. And if you recall the second quadrant, the x value or the base of the triangle here, which is actually just our adjacent side, would in fact be negative because our x values here are negative and the adjacent side is negative. So the hypotenuse in this case, so we have the opposite, which is here, which is positive, and the adjacent, which is negative. And if we were to do tangent, which is equal to the opposite over the adjacent, we're actually taking a positive opposite and multiplying it to a negative adjacent, the resultant of which would actually lead to a negative answer, thus proving that the cotangent in the second quadrant is in fact negative. So that would have to be negative in and of itself completely. So that's essentially how you solve these types of problems. You want to locate the angle in which quadrant it's in, and we're usually given that. And then, of course, determine the sides of the triangle, use the Pythagorean theorem to solve, and then once they're solved, we'll plug in for the trigonometric functions in question.